These are the conditions for a valid mechanism. The elementary steps in the mechanism have to add up to the overall reaction. And the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. Elementary steps are chemical equations that describe when the particles actually connect with each other, when they collide and react. And so because of that, we can write a rate law for an elementary step by just looking at the elementary step equation. We can only do that for elementary steps. Yes? Why? Because in the overall reaction, we don't know exactly what's happening. A lot of these things happen in 2 or 3 steps. And because the overall reaction doesn't tell us that, we can't tell if it's first order in this or second order in that or anything like that. The elementary steps, which really are sort of made up, right? They're a hypothesis. We think that this happens and this happens and that happens. And with a lot of really hard study, you can figure out for sure what's going on, but mostly we don't bother. We look at the elementary steps, and we know that the slow step is the one that has to limit the rate of the reaction. And so we can calculate the rate law based on that slow step. And that rate law has to agree with what's experimentally determined. And then we say, this appears to be a valid mechanism. It doesn't prove anything, but it's consistent with observation. Any other questions? Because this is kind of a hard thing to get your mind around.
I think mainly how to do it. I think we did it in 2 slides before.
How to get the overall rate law from the individual. Yeah, we're going to do some more of that.
Okay.
Yeah. So if the mechanism starts with an initial fast step, then the rate limiting step, which is not the first step, it's going to be the second or third or whatever, is probably going to have intermediates in it. And so you write the rate law for that slow step. It's got intermediates in it, and you can't use that as the rate law for the overall reaction because it's got a species in it that you don't know the concentration of. So that's just not going to work. But what we can do is we can understand that if that first step is really fast, you can actually get an equilibrium established between the reactants and products of the first step. And so we can do some math with that and express the concentration of an intermediate in terms of the concentration of one of the reactants. So this one, we're saying, show that condition 1 is met. And we went through this, we added these 3 things together, and we get this law up here. Then the next one was show that condition 2 is observed. So here we have the rate law predicted by the mechanism. We've got a fast step and a slow step. And so what we can do, because if we express the rate law for that slow step, let me just write it over here. Rate equals a rate constant times the concentration of H2. The coefficient is 1. The exponent is 1. For elementary steps only, H2O2, again, coefficient of 1, exponent of 1. So this is the rate law for the slow step. But this has Okay, what did I do there? You see what I did there? Yeah, I'm like, oh, how do we do that? That's not actually going to work. This is N2O2. Yeah, we can't express H2O2 in terms of other things because it's not even in this reaction.
So is N2O2 an intermediate?
Yes. N2O2 is an intermediate. It is formed in this first fast step. And then it goes on to react with H2O. So it's formed and destroyed. It's not originally there, and none of it's left at the end. And so we can't have its concentration in the rate law. It makes the rate law useless. This is fast, and as we'll learn in the next chapter, almost all reactions are at equilibrium at some point. The equilibrium may lie very far to the right or to the left, but almost nothing goes completely all the way. So it's very reasonable to say that this is establishing an equilibrium. So we can look at this first step and say, well, if it's at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So the forward reaction is 2NO going to N2O2. That's an elementary step. We can write a rate law for it. We'll call this rate forward equals K forward times what? NO squared. Because there's two of these. Okay? The reverse reaction is that flipped around, it's N2O2 going to 2NO. We can also write a rate law for that. Rate reverse is equal to K reverse times what? N2O2. Now, we do not know what these rates are. We don't know what these rate constants are. But we know that this rate is equal to that rate. So then we know that K forward times NO squared must be equal to K reverse times N2O2. You okay with that? At equilibrium, the forward reaction and the reverse reaction are happening at the same rate. So we can set these two terms equal to each other. Now we have an equation, and we can solve this for N2O2. So I'm going to divide by Kr on both sides. So now I can see that the concentration of N2O2 is equal to K forward over K reverse times NO squared. This is the rate law from the slow step. This is the rate law that we can't use because it's got an intermediate in it. But now we have an expression for the intermediate that we can plug in here, so we don't have intermediates anymore. We just have a whole bunch of K's. So we have rate. Yes. Yeah.
How do you know when it's an intermediate?
How do you know when it's an intermediate? That's a good question. So the overall reaction is not on this slide, unfortunately. But I think it's 2NO plus H2. Let's see. 2NO plus H2 going to H2O plus N2O. N2O2 isn't in this. Because it's a species that gets formed during one of the steps and then reacts and makes something else so it goes away. So it's formed and destroyed. It's in there, but we have no way of knowing what its concentration is. Its initial concentration is always going to be 0, and so that's super not helpful. Does that help? Yeah. So we can take rate equals K H2, and then instead of this, we're going to plug this thing in. KF over KR NO squared. I'm going to collect all of these K's. That's not an R, that's an F. And we can just lump those all together and say that is the rate constant for the overall reaction. It's the combination of the rate constant for the mechanism of the slow step and the forward and reverse rate constants for the initial fast step. But we don't know what any of those are, and we actually don't care, because all we want is the rate constant for the overall reaction. So we take all those pieces and we lump them together and we say this is the rate constant. Did that help?
So the slow step limits,
Right.
which is why you use
Yeah.
Yes.
H2.
It's like that slide we had of the freeway, where there's some construction, and 3 lanes come down to 1 lane. That's the slow step. Getting past that point is what limits the speed of all the traffic, because you can't go faster than the slowest step. It doesn't matter what comes before or what comes after. Those are faster. It's just the rate limiting slow step that matters. Any other questions?
So I know that we can't use the rate law of KH2 and N2O2 because it's an intermediate.
Mm-hmm.
Where did we switch it? Like, where's the, what can we use instead? And then how?
So we can use, this is the rate law for the slow step, right? And we couldn't use this. So we can look at this first fast step, say, well, there's a very good chance that that's at equilibrium. At equilibrium, forward rate equals reverse rate. So we can take these rate laws that we get from the forward reaction and the reverse reaction. The rates are equal at equilibrium, so we can set them equal to each other and express N2O2 in terms of NO instead.
Okay.
And then, so we did that, and then we substitute this in up here.
Got it.
And it looks like, some math voodoo, but it's not. Yeah.
So the main reason we're doing all this is because we started with a fast initial step.
Mm-hmm.
So would we have to do the same thing? We wouldn't have to do the same thing if we started with a slow step.
No, if you start with a slow step, you're good. It's just the fast ones. Anybody else? If I remember correctly, there's some more things about this coming up, some more examples. Okay, so here's the reaction of ozone decomposing to oxygen. Here we have the experimentally determined rate law. And we are supposed to look at this proposed mechanism and show that it's consistent with this rate law. So we have a first fast step, so we can write the rate law for the slow step from its equation. So the rate is equal to a rate constant. And how do we finish this out? So we've got concentration of ozone, coefficient of 1, concentration of oxygen, atomic oxygen, coefficient of 1.
Okay, so now we're gonna have to convert.
Right, because we have this intermediate. The atomic oxygen is an intermediate. And so we're going to look at this first fast reaction and say, well, this is at equilibrium. The forward rate is equal to the reverse rate. So forward rate forward is equal to forward rate constant. And so we're going from O3 to these guys. So that's just going to be the O3 concentration. Everybody okay with that? And then the reverse rate is, we'll just call this KR, is what's going to go here? Concentration of O2 and O. Right? At equilibrium, these rates are equal. So these terms are equal. Everybody okay with that? So the thing I'm trying to get rid of in my rate law is this intermediate O. So I'm going to solve this equation for O. So I will divide by KR and O2 on both sides. These guys cancel out. So the concentration of O is equal to this ratio of rate constants, O3 over O2. So I'm going to take my slow reaction rate law, and that had O3. And now instead of this O, I'm going to plug this in. So K forward over K reverse times O3 over O2. Yes?
Can you just skip moving the KF and KR since they're different?
Yeah, you really can.
Okay.
You can just say, well, I know there's all these Ks, and I'm going to lump them all together at the end, and so is this K. But that bothers some people, so I'm trying not to skip things. But that's an excellent question. So now I'm going to collect all of these Ks into one group, and I'm going to say that the rate is equal to the rate constant. Now I have O3 times O3. So that's O3 squared divided by O2 concentration. Is this the same as that? It is. It's written in a slightly different form. I wrote this in the denominator instead of in the numerator with a negative exponent. But it agrees. Questions? Yeah.
Yeah, so at the beginning of the chapter, it stated that the rate law is applicable as long as the reversible reaction is not the rate magnitude. So how come we can apply the rate law to this problem?
So we aren't looking at the rate the overall reaction that we're looking at is not very reversible. It mostly goes to completion. The individual steps may be at equilibrium, but the overall is not. So good question. Yeah.
I'm confused. So where did, when we go from O, you know how we divided by KR?
Mm-hmm.
O2, where did the just regular O go in the next step?
So let's. Wish it would do. It doesn't work that way. It's okay. So we found that O was equal to this. I just cleaned up the equation. And so here, instead of O, I'm going to write this. Any other questions? Once you see it, it's not hard, but you just have to see what's going on. And sometimes you actually have to, write the stuff out yourself. Yeah, question?
If we're given a question like this on the test, all we'd have to do is just show like our work equal to the experimentally determined rate law.
Mm-hmm. Yeah, so for showing your work, say on an exam, I'd want to see this rate law for the slow step. Something here expressing the forward and reverse reactions for the fast step being equal. And then substituting in and getting the final one.
How did the O get on the other side?
How did the O get on the other side?
Yeah, so KF equals KR, right?
No,
No?
the rates equal each other.
Okay, that's what I meant. Oh, never mind, the O is with the reverse rate, not forward rate. Got it.
That's okay.
Just thought that.
Yeah, you gotta figure it out. There's a lot of O's in here. So many O's, right? Oh. Any other questions about this one? Predict the overall reaction in rate law that results from the following two-step mechanism. Well, the easier part is the overall reaction. How do we find that?
Cross out the products.
Yeah, we're going to add these together and cross out things that are the same on both sides. And those will be the intermediates. They get formed and then destroyed. So here, the A2 is an intermediate.
The only time a fast step can be at equilibrium is if it's first. Is if it happens first.
That's a safe thing to say. There's, in case you haven't figured it out yet, we lie to you a lot in general chemistry. And being a scientist, I try not to make statements that are not actually true. And so I qualify things. So I told my students in 1A yesterday, in Chem 1A, all ionic compounds have one cation and one anion. That's not actually true. But in 1A it's true, right? So in Chem 1B, you're okay with that idea. Yeah.
Okay, so like temporarily.
Yeah.
Okay.
It's, yeah, I don't know if it would matter at all, but that's going to involve way too much thinking on my part, and I know it won't matter for this class.
Okay.
So we're going to add these together. And so we see that A2 is formed and A2 is destroyed. That's the intermediate. So we write down what remains. 2A plus B forms A2B. And that's the overall reaction. what's the rate law? Yeah. Rate is going to equal the rate constant times the concentration of A squared. The first step is slow. The first step always only has reactants in it. It can't have an intermediate in it. So we can write the rate law for that slow first step, and that's the rate law for the whole thing. Here's the overall reaction, though. There is a reactant B. But what does this rate law tell us? Zero order for B. The concentration of B does not affect the rate, because the slow step is having two A's collide with each other and react. That's what takes the time, and after that, everything else is faster. So concentration of B doesn't matter. Any questions? We did the hard kind first and then the easy one.
What did it be times B?
So we can't write the rate law from this reaction, because this is the overall, it's not
Just the
elementary steps. We can only write them from elementary steps in the mechanism. Here, the slow step, which is the thing we're always going to start with, this is the rate law for the slow step. It doesn't have an intermediate in it, and so we can just use that. That's going to be for the overall reaction.
So we could have written that first?
We could have, yes. But the other stuff we were doing, writing the rate law, was complicated. So we started with what seemed to be easier. Any other questions?